record and click here and let Rich go for it.
Oh, okay. I'm live now?
Yep.
Okay.
Go.
Okay. Let's see. I'm going to advance slides with this.
Yep.
No, okay. This. Okay, everyone. So it's the last session of the day, and I will be doing the first part of the presentation. Then I will hand this briefly to Zhang, and then she'll hand it to Karl, Rupp. So I'm going to talk about understanding and tuning performance in PETSc on emerging many-core architectures, but also a lot of this really applies to just traditional architectures as well. I'm going to talk about kind of the driving forces behind some of the hardware architectural trends we've seen, and what those mean for us when we are tuning our software. Then I'll talk some about performance modeling, PETSc profiling, and then some specific things that we're doing in PETSc to support many-core architectures. And I'll talk about some practical examples that use the second generation NiceLanding Intel Xeon Phi. So I wanted to start with a little bit of background on what's really driving the current trends that we see in HPC. For over 50 years, one of those things has been Moore's Law, and I was an Intel employee till about a year ago, so we heard a lot about that there. It wasn't how if you go back and you look at the 1965 paper, it wasn't stated this way, but basically when everybody says Moore's Law, what they mean now is that transistor density doubles roughly every 2 years. I keep seeing things about how Moore's Law is dead, but I think that reports of its death have been greatly exaggerated, though there has been some slowdown in the cadence that they have at Intel. For decades, the single core performance has roughly tracked Moore's Law growth because smaller transistors can switch faster. So we had Moore's Law, and the other thing that was really helping us out and giving us kind of a free lunch was Dennard scaling. So in 1974, Dennard observed voltage and current are proportional to the linear dimensions of a transistor. Therefore, the power is proportional to the area of the transistor. And this works actually really well until you get down to about the 65 nanometer feature size, which we hit in like 2005, 2006. And the problem is that when Dennard came up with his scaling analysis, it ignores the leakage current and the threshold voltage. And when you get down to 65 nanometers, this breaks down and power density starts to increase because the leakage current and threshold voltage don't scale with the feature size. So my thesis is really that a whole lot of what's driving everything in novel and emerging high-performance computing architectures is really all just comes down to power considerations. Because this power wall that we hit in 2006 has limited practical processor frequencies to around 4 gigahertz. And so, of course, increased parallelism has become the way forward. And a nice illustration of this is provided in this slide from Karl Rupp's excellent blog, which you can go look at. There's the URL down there. And let's see, do we have a pointer up here? Or does this work? I don't know. How'll this go? I'll point. Okay. So you can see actually a lot of the trends that I just talked about. With the breakdown in Dennard scaling happens about right here. And so the number of logical cores goes up a whole lot, whereas the typical the frequencies level off, and unfortunately the typical power had to kind of stay about here because they're just cooling considerations. You're going to melt your motherboard if you go too much higher than that. So pretty much we're limited to like a couple hundred watts. And of course the transistor count keeps going up, and what we have to do is just more parallelism. So that's really what's driving what we see. So what this means for, in terms of practical considerations is that, these emerging architectures that are coming out in the last several years are getting pretty complex. You've got a lot of hardware cores, a lot of hardware threads. You have wide SIMD registers. You've got increasing reliance on, things like fused multiply add units, with multiple execution ports. Intel is proposing a quad FMA instruction, so you have like 4 packed FMAs for a special instruction that does those. And you're seeing the emergence of multiple memories to manage. So like on the NiceLanding processor, which I'll talk about a little later, there's normal DRAM, and then there's a special high bandwidth DRAM. There's now byte addressable NVRAM, non-volatile RAM, that's also being introduced. That adds another memory that you have to manage. And of course, there are multiple NUMA nodes. You have to worry about host versus device memory. Just a lot of stuff going on that you have to worry about. And this is also accompanied by a growing depth of hierarchies in the memory subsystem, in internet connect topology, even the I/O systems. So they're getting pretty complex, and they're getting pretty hard to program. You've been hearing a lot about vectorization the past couple years. Intel's done a real PR blitz on this. But the vectorization at its kind of best case, it often requires fighting the compiler. In the worst case, you have to really entirely rethink your algorithm. And when you do all this, you also have to make sure to balance the vectorization with cache reuse, which sometimes people get so wrapped up in making their code vectorized, they forget that they're doing some loop transformation that starts blowing out their cache, so they get no benefit from all their vectorization work. There's also the host versus offload complexity, and part of the wrapped up in sort of the power consideration issues is this growing imbalance between the memory bandwidth on a device versus between the host and the device, and basically the balance in flop rates. The growth in peak flop rates have really greatly outpaced the available memory bandwidth. So I'm going to talk some about some performance tuning strategies for dealing with these trends. So it really comes down to, in the world that we live in PETSc, is flops in memory bandwidth. So the operations in PETSc tend to deal with pretty large data sets, and they don't perform very many arithmetic operations per byte that's loaded or stored from main memory. So this arithmetic intensity is usually below 1. Modern CPUs at full utilization really want to support like a arithmetic intensity around 10. Of course, we're memory bandwidth limited in PETSc, and I'll talk some about how we know this a little bit later in the talk. So what, the really primary consideration now when you're trying to optimize your PETSc code is just maximizing the use of the available bandwidth. So I'm going to talk a lot about process placement. This is very critical on the non-uniform memory access systems that are becoming more and more common. And then there are also things that I guess we hear a lot anytime you take you go to a class and they talk about optimizing your code, contiguous blocks of memory, avoid unordered reads. These things have been true for a long time, but they're just increasingly important now that we're really starved for memory bandwidth. And again, I'll point out the vectorization doesn't matter if poor memory bandwidth utilization makes your VPUs just sit idle waiting on those. So a typical question that we get from new PETSc users is, I have I bought a new 20 core Xeon system. Why don't I get a speed up of 20 with my PETSc code? And it really comes down to what this stream triad benchmark tells you. So the stream triad is a very commonly used benchmark that basically does this. It works with 3 vectors. Y plus scalar times x, then you assign it this w. And you do this with very large arrays that won't fit in cache. So you're really just, all the traffic that you're doing is from main memory. And this usually saturates pretty quickly. Like on most modern CPUs, you might hit it with 8, maybe 16 processes per threads on most modern CPUs. And then after that, you really don't get much gain after the saturation point. And there are a few weird things like, the NiceLanding with the this multi-channel DRAM saturates much later, but it's a real outlier here. So this thing is for strided memory access. Sorry, a stride 1 memory access, which is a nice contiguous memory access. I want to point out this for your particular problem, this may even be worse because you may actually have to do something where you have non-unit stride access, and you see no architecture is like this. Every architecture does not do well with that. So you want to try to avoid that as much as possible. For this reason, if you have you're working with a bunch of, say, C structs, you don't want to deal with arrays of structs. This is something that you've been hearing about in, whenever I see somebody like, I don't know, John Levesque from Cray talk about this, he always talks about you don't want to have arrays of structs, you want structs of arrays, and it goes back to this problem here. So you don't want this, you want to do something like have structures of arrays. Okay, so this actually, I think this may actually be an example from like a PETSc user post actually, because again, people ask questions like, why am I not getting a speed up of 24 on here? And you can actually figure out what your system might be able to give you by doing, once you've built your PETSc, set your PETSc arch correctly, and make streams, PETSc dir. And so for this 24 core one, it looks like, well, you're going to get a lot less than 24. You get about a max speed up of 4x on this machine when you're running a typical PETSc app with multiple MPI ranks on the node. So, most of your gains are going to be hit when you're already at 4 to 6 ranks. So if you have a cluster of these and you want to use more than 6 MPI processes, hopefully you can start putting those onto other nodes in your cluster. So the trends that we're seeing kind of exacerbate this problem because, as we add more cores to the system, you end up, you can only put like so many cores on the CPU, so you have multiple sockets. And so modern compute nodes are typically multi-socket. They'll have at least 2, maybe 4 sockets. And what this means is that you have non-uniform memory access on your CPU. So the process running on, that's running on one socket has direct access to the memory channels of its CPU. But requests for memory attached to a different socket have to go through the interconnect. And this interconnect may be a ring bus, or in like NiceLanding or the new Skylake server, it's a 2D mesh, but it's some kind of interconnect that sits on the motherboard. And to maximize the available memory bandwidth, what you need to do is make sure that your processes are distributed evenly between the sockets. Like you don't want to, as you're doing your scaling problem, you don't want to load a bunch of processes onto one socket and then you're only getting like half your memory bandwidth. So here's just an example running on a system with 2 sockets, 6 cores per socket, 2 hardware threads per core, where let's see, I think this is OpenMPI. I can't remember which particular MPI distribution this is, but it offers a bind to core option. And if you do a mapping by core and you run stream, you get about half of the bandwidth, well, a little bit better than half the bandwidth that you get when you make sure to tell your MPI distribution to spread things evenly between the sockets. Unfortunately, I found in practice you can't assume that your MPI run defaults to sensible placement. I really wish I had a pointer. I should have brought a pointer. So over here, when you just run make streams on this system, you can see that what's happening is it looks like the MPI is defaulting to putting all the processes on one CPU until finally it runs out of logical cores on there, and then it starts using more of the system. So you get this kind of like plateau of your available memory bandwidth, and then it bumps up a little bit. And you actually need to specify this binding option here to get good memory bandwidth. It actually gets more complicated because let's see, the previous system here we're considering, this is a pretty simple system. It's just got 2 sockets and 2 NUMA domains. And inside that system, there's one L3 cache that's shared by all the cores within a NUMA domain, but that's actually not true on like a bunch of AMD Opterons, and you have shared caches on the NiceLanding as well. Let's see. Okay. So something like NiceLanding has a more complex design, and you can see here there's a portion of the. I can't point. Sorry. So this is a portion of the LS topo PNG output for a KNL node showing 2 tiles. So the KNL is arranged where there are 2 tiles, or multiple. There's a network of tiles, a mesh of tiles, and each tile has 2 cores, each of which has 4 logical threads. And the cores each have an L1 cache, but they share an L2 cache. And so you actually have to be, let's see. Okay, let me back up. What I'm trying to say is that because of increased sharing of things like L2 caches, you can't necessarily get the best performance just by making sure that you distribute your MPI processes evenly amongst the sockets. You actually have to be careful about how the placements happen, within the socket. And I actually have an example here where I use 2 different. This is with on a KNL node, and I'm using Intel MPI. And Intel MPI offers this environment variable, this IMPI pin domain, and it has some kind of like shortcut options to help you do some sort of usual mappings you might do. So above, I'm saying that MPI pin domain is auto compact, and what auto means is auto means to automatically determine the size of each domain that I'm going to pin a process to. And this is just based on how many MPI ranks I'm running and how many cores there are to divide them between. So I'm keeping that the same between these. But there's this compact or scatter thing that says how I'm going, once I've chopped up things into these domains, what order am I going to assign logical processors to each domain? And in compact, we're trying to make all the things very close together, whereas in scatter, we're actually trying to make them far apart. And in this case, the compact mapping gives you almost twice the performance of the scatter mapping. And if you look here at the, it's a little hard to translate all these into actual cores. But let's see, up above on the first row, rank 0 is on logical cores 0, 68, 136, and 204. And if you actually were to look at the LS topo output from HWLoc, you'd see that those are all logical threads, those are all hardware threads on the same core. Whereas down here, we've used this scatter mapping, and the first 4 MPI processes are running on, let's see, this belongs on core 1, that's also or core 0. This is part of core 0, this is part of core 0, and this is part of core 0. So we're doing, really basically the exact opposite of what you want to happen. And this is, we're not doing any real weird mapping. We're just using one of the mappings that, Intel says, hey, you should just try this mapping. So we try that, you get very bad performance. And so placing consecutive MPI ranks on cores that share the same L2 cache, in this case, is, that's what we want. It benefits performance because the 2 ranks communicate frequently with each other, and the latency between the cores sharing an L2 cache is a lot lower than if they're not sharing one. But some other codes, you actually don't want to share the L2 cache because that increases the total L2 cache capacity and bandwidth available to the application. So there's this trade-off you have to consider between placing things close together to optimize for efficient communication and synchronization versus farther apart to maximize available resources. Unfortunately, the strategy, kind of depends on the application and the software and the hardware stack. So you need to experiment with this. I really encourage everybody who is going to do this to use the portable hardware locality or HWLoc software packages ls topo command because the numbers that are assigned to the logical processors are very hard to interpret, and you need this to actually show you what the topology is. And if you don't have this on your system, PETSc's configure can download it for you. Okay. There's a lot more in the PETSc manual. Karl, Rupp, and I did a fair amount of work on that maybe 6 months ago on adding a big discussion of all these process placement things that you have to consider. Part of why I felt that was important was actually when I was an engineer at Intel, and we would have customers come to us saying that their code wasn't performing how they wanted it to. Maybe like half of the time, we found that the most important thing to do was actually not to touch their software at all, but just to make sure that they had a proper process mapping, and then that would give them a huge speed up, actually. So it's actually becoming a very important issue for performance. It's really actually very hard to interpret as a user. So look in the manual for more details on that. Okay, I'm going to talk some now about performance modeling and performance profiling. So because it was sort of natural to talk about the process placement issues when we were talking about the HPC architecture trends, I got a little bit ahead of myself, and I started discussing several strategies for dealing with the memory hierarchies and the flop byte balances trending with Manycore CPUs. But really, before you do any performance tuning, I always try to consider these two rules that I consider very important to follow. Rule 1 is don't try to tune or optimize code performance without meaningful performance measurements, because otherwise you can waste tons of time optimizing for some problem that's not actually a problem. And then rule 2 is don't think that you have any meaningful performance measurements if you don't have a performance model. You need some kind of model to help you verify your implementation and to give you some understanding of why the performance is what it is, and why things are behaving that way, and how it can be improved, because otherwise you're just sort of doomed to randomly trying things and hoping that they make the code faster. So even a very crude approximate model is better than no model to guide you in this. Karl put together a list of like his bottleneck potpourri. One of the bottlenecks we deal with is latency, bottleneck in the strong scaling limit, and it's usually the ultimate limit for time stepping codes. And there are a lot of sources of latency. There's the network latency, PCI Express latency. There could be latency on your QPI interconnect or your mesh interconnect, like talked about on a NUMA system. Thread synchronization can actually be extremely expensive on some systems, like the first generation Xeon Phi had extremely costly thread synchronization. And of course, there's the memory latency. And then also, you have to think about bandwidth and the arithmetic intensity we already talked about, the number of flops per byte. And let's see, the theoretical peak floating point operations per byte in double precision have gone up a lot, and that doesn't really help us that much because we tend to not operate in these areas with our PETSc algorithms. We're usually at an arithmetic intensity that's smaller than 1. So you can come up with some analytical models that just make some very simple assumptions, like this is a slide from Karl where he's just x. You have a vector x equals y plus z, and you can just do some calculations on the back of an envelope, and you can get this this simple expression for roughly what's limiting this, and it's the memory bandwidth. And you can do more complicated analyses. I encourage you, if a really good paper is a 1999 paper. This is actually a link to it if you download the slides, where Bill Gropp, Dinesh Kaushik, David Keyes, and Barry did a very nice analysis of the cost of a sparse matrix vector multiplication. So, oh, sorry, I thought somebody was asking a question. So, it's hard to come up with performance models for some of the things you might do in PETSc, like if you're doing geometric multi-grid and you're doing matrix triple product to determine your prolongation operators. That's pretty hard to model, but things like matrix vector multiplication, that's a little easier. We can't come up with really exact models because the hardware is getting so complicated. But even these sort of cruder models are very useful for understanding that really we're very bandwidth limited. So I'm going to talk about profiling now, because you have to have a model and you need to have a profile before you do any optimization. So before I do that, I want to point out this is something that trips up a lot of new users. You need to be careful to make sure before you do any profiling work that you're actually using an optimized build. PETSc's configure when you configure PETSc and you don't tell configure otherwise, it defaults to a debug build. The debug build is really useful. It captures a lot of useful logging information. And all of your development work should use a debug build. But when you want to do performance work, you need to turn that off. So you've got to tell it -- with -debugging equals no. And you also need to ensure that your compiler is generating optimized code. I'll note that a lot of compilers like GCC actually defaults to doing no optimization whatsoever, whereas, say, the Intel compiler is actually fairly aggressive. So before you do a bunch of tweaking your code, I think you should actually just explore different levels of optimization. Most of the compilers have a -O that groups together a whole bunch of optimizations at just in different levels to make it easy to explore them. I'd say to consider try those, and then also consider some value unsafe optimizations that do things like instead of always doing a floating point divide, they compute a reciprocal of something and multiply by that. They're value unsafe, but they can really make your code a lot faster. And again, they're usually flags like in GCC. There's -ffastmath in the Intel compiler. There's this FP model that you can FP model fast that turns on these. Try these, but then again, do make sure to verify that your optimized executable is actually still correct after doing these. But try all these things before you start hand optimizing your code. The other thing I want to point out, and this also trips up a lot of people, is that new compilers generally won't use things like advanced vector instructions by default. They default to older instruction sets that are going to be found on all the processors, not the things on your cutting edge one. So if you're using a NiceLanding processor in GCC, you can specify this march equals KNL, or you could say march equals native, but this tends to trip up a lot of users because on a supercomputer, they're often cross-compiling. The login nodes you compile on are not the same as the back-end nodes. So if you say march equals native on your compile node, it's not going to optimize for the instruction sets supported by the actual compute node. I also want to mention that we have done some work that showed up in the latest PETSc release with some hand-coded AVX512 kernels. We didn't feel like turning these on by default, so if you want to use them, configure with this option. And this is actually, it's in all the example scripts for NiceLanding systems. So make sure you do all that before you do any profiling. And the other thing you want to do is make sure that you have your math right before you do a bunch of profiling. So choose an algorithm that you're sure really converges and that gives really robust iteration counts. I've encountered some cases where a poor graduate student really wasted a lot of time optimizing code that turned out wasn't numerically correct in the first place, so make sure you do that. And then once you've done that, you can do some profiling. Matt already talked a little bit about using log view for performance profiling. Matt covered, I think you already covered all this, didn't you, Matt?
Yeah, at least the interface for the logging I covered.
Okay, yeah, so I'll kind of go.
I didn't show the output though.
Oh, okay. So you get a lot of useful output from log view. It can be a little overwhelming when you first look at it. The first thing is look at the top of your log view, and you'll just get a summary for kind of for the. You get a nice summary before a breakdown that breaks it down into lots of events. So you can just look at this, and then there's also these summaries per stage, and we also track memory usage per stage, time, for each event you're logging, the number of messages sent, the number of those that were reductions, and also, the flops per event per stage. And so the default, it looks like this. It's a little hard to figure out at first, but let's see. So here's, this gives times. You also have some information, some basic information about load balance here, because you have these maxes and ratios for all these things. So you can see if this appears to have this with 6.4 has some kind of load imbalance in that operation. Not surprisingly for a vec_scatter end. You have flops, and here we track the messages, average length of the messages, and how many of these were reductions. And then we also have these breakdowns into percentages of like the time spent globally for your whole PETSc run versus in the stage that you're doing. I actually really like to look at these last columns over here with these the message stuff. This can be really useful, especially figuring out if you see you're doing a lot of reductions and something seems to not, the time spent in these things with reductions grows a lot as you try to strong scale. You need to really think about doing something about the latencies. And as you're doing strong scaling on like a big, massively parallel system, this is usually it's what I've always hit eventually. And it's these reductions that occur in things like vec dot, vec m dot, vector norms, vec assembly begin. If you find these are really a limiting factor, you should try to use a KreeLog method that, like one of the several pipeline KreeLog methods that have been implemented, or the improved BiCG stab, which is sort of BiCG stab, but makes you only have to do one reduction per iteration. I think Matt talked about how you add logging events. Anyway, it's pretty straightforward. You can look at it in the manual. Something that I think is very useful in PETSc, and actually I find a big limitation of a lot of tools that are just profiling tools, is PETSc has this idea of logging stages that most profiling tools don't have. And I find it really useful to have this, this is actually a portion of a log view from pFlowTran, a subsurface flow and reactive transport code that I work on. And most pFlowTran runs have a flow solve that happens, and then they have a reactive transport solve that happens. And if I take this code and I try to look at it just using something like the Intel vTune profiling software, I can't really get much useful out of that, because if you look at the time that's spent in my KSP solve in the transport stage and the KSP solve in the flow stage, very different things are happening. In this particular example, the flow solve is much smaller than the transport solve. I'm really solving very different things, but if I look at this in vTune, it mixes up all of my time spent inside the KSP solve, my matmults. It just all gets convolved together, and I can't figure out what's going on. So in PETSc, it's great that when I'm going to do a flow solve, I pop onto my stack. I'm going into the flow stage, and then I pop on the transport stage when I'm doing this, and it separates all these things out and makes it possible for me to interpret this. I really wish that other profiling packages let you do this easily. I think this is a really fantastic feature in PETSc that you should use when you are putting in profiling stuff for your own code. Okay, the last part, I'm going to talk some about support for many-core architectures. With some practical examples from NiceLanding, because that's the only real many-core architecture that I've actually had available to work on. So I'm going to talk a little bit about what NiceLanding is, and I'm going to talk about some out-of-box experiences with PETSc on NiceLanding. And I'm going to talk about some new features in PETSc targeting many-core. There's a sliced LPAC matrix class. Also, I've got a matrix class that I added recently that leverages the Intel MKL sparse BLOS. And then I'm going to hand over for Hong to talk about some of the MPI3 shared memory implementations of vec_scatter that she's done. The NiceLanding is, well, it's an orphaned processor because the third generation NiceLanding was canceled. But this is still a relevant thing to talk about because, one, we're actually stuck with NiceLanding supercomputers that we're going to be using for the next couple of years because we're not getting an upgrade till then. So it's still useful to know how to do it. But also, a lot of the things that first appeared in NiceLanding, like this mesh interconnect and the AVX512 instruction set, have made it into the mainline, Intel's mainline Xeon server processor line, because the Skylake Xeon server has this mesh interconnect and has AVX512. So it was still useful to think about this stuff. So KNL has a lot of lightweight cores on up to 36 tiles interconnected by this 2D mesh. I think the thing that's really interesting about it from a programming perspective for somebody doing high performance numerical linear algebra type stuff, sparse linear algebra, is this high bandwidth memory they introduced. This is an on-package memory that gives really very high bandwidth, up to like 490 gigabytes per second bandwidth on the Stream Triad. You can actually work with this memory in a few different ways that you have to choose at boot time how your KNL sees this. And usually you want to either expose it as a separate NUMA node in flat mode. It's a NUMA node that has no processors that live in it. And you can explicitly move things in and out of this NUMA node, or you can just choose to treat it as a massive direct map L3 cache in cache mode. For highest performance, you actually want to do this, because this actually works. The cache mode works surprisingly well, but you get the best performance actually treating it as a separate NUMA node. So that's what I do in the examples here. So actually, people have asked, does PETSc support Xeon Phi? And I usually tell them, well, it actually works just okay as is. So this is an example. It's the KSP tutorial example 56. It's a linear elasticity problem coded up by Mark Adams. And yeah, I'm just running it with the PETSc default solvers, because a lot of people, they don't know what to do. They just run the default solvers, so I thought I'd do that. So I run with the default solvers, even though this example is actually a great example for using the algebraic multigrid. But first I try running it like this. And I compare it against, let's see, this is a standard Xeon. This is a Broadwell Xeon machine. And then KNL, where I'm running with everything in DRAM, which is the slow stuff, or everything in this 16 gigabyte MCD RAM. And this is lower is better on here, because this is wall clock time. The KNL looks really good here, and it's all because of the memory bandwidth that you get out of MCD RAM. And I put here some of the breakdowns of what you get from the PETSc log summary, the time in GMRes, orthogonalizations, matrix multiplication in MatSolve. And let's see, down here I'm running out of DRAM. All these things look really good. The story isn't quite as good when I use a more sophisticated solver. So I run the same example using the GAMG algebraic multigrid solver. And you find here it's kind of a mixed bag. Like the setup phase on KNL is really slow. But once you get it set up, the solve phase is actually really fast, because it can really benefit from the memory bandwidth there. We're working on some new AVX512 optimized sparse matrix multiply stuff that Karl Rupp's doing, so maybe we can make this go a little bit faster. But the overall performance is okay on this. There's a mixed bag. There's certain things that look really fast on KNL and certain things that look really slow. It averages out to be, a decent platform for PETSc without you having to really do too much, actually. So that's encouraging, because on the first generation Xeon Phi, nothing worked well out of the box, ever. So this is pretty encouraging to me. I put in here an example from pFlowtran that just shows similar kind of stuff, where some things are very good on here, like the orthogonalizations inside GMRes are very fast on KNL, but forming the Jacobian is not as fast. Things work out, so the KNL is a little bit faster than the Xeon on this. Again, it's sort of a mixed bag. So one of the things that showed up, like in this pFlowtran example, is we'd like the mat mults to go faster than they do. And the default AIJ matrix format, which is compressed sparse row format in PETSc, it's very versatile, but it can be poor for SIMD. And there are two main disadvantages to using this representation. The first is you can get poor utilization of the SIMD units when the number of non-zero elements in a row is less than the vector register length, or when the number of non-zeros modular register length is small and positive. So if you're in double precision, you can fit 8 doubles in a KNL register, and if you have 9, that's bad because you get good utilization on those first 8, and then you have to do a whole other loop iteration where you're only using one element of that 8-element vector. Also, the sparsity pattern of your matrix can lead to very poor data locality on the input vector. So to enable better vectorization, we and principally Mr. Herr Dr. Hong Zhang, the Hong Zhang who couldn't make it here, added a new matrix class to PETSc. It's a sliced LPAC format. And it doesn't support, I said it's not as versatile as AIJ. Like it doesn't support, ILU preconditioner. Basically just does, variants of matrix vector multiplication and also forming Jacobian SOR smoothers. So we added this, and we provide AVX and AVX 512 intrinsics implementations of this. And if you construct things right, this can actually give you pretty good performance. So this is from an example, this time steppers advection diffusion problem here, which we run with multi-grid preconditioner, and the preconditioner, on each level we use a Jacobi smoother, and also use Jacobi on the coarse grid. So there's nothing that the sliced LPAC is bad at doing. This is very, very fast because it's for these MatVec type operations, it really screams. And so when we do this, we get like 2x performance that of AIJ. So that's pretty good. And memory bandwidth actually saturates with 58 processors. And if we look at this on a Roofline plot, probably a lot of you have seen these. They become very fashionable over the past few years. They just sort of give you they're sort of a conceptual model for really what the best possible performance you can get, based on basically, how many flops per byte you can do. And we're getting basically right at the Roofline here with the sliced LPAC format. So this is very good for, this is a 5-point stencil, so really short matrix rows. If you're working with, some high order thing where you have, like 80 non-zeros per row, this doesn't really help, and AIJ actually works pretty well, especially with the hand-coded AVX 512 intrinsics implementations that we added recently in PETSc. This is just showing the same thing again, but running it on a much bigger problem on 512 nodes on Theta, the KNL machine at Argonne, so it still works when you scale it up. The other thing that we've done is I've done a lot of work adding a new matrix class to PETSc to take advantage of the sparse BLOS work that has been going into recent versions of MKL. So we have this AIJ MKL and a B AIJ MKL for its block matrix. This facilitates use of the new sparse inspector executor routines that the sparse team of MKL has been adding over the past couple of years. And this inherits from the AIJ matrix, but it just overrides some methods to call MKL routines. If you've got a code that uses AIJ, it's pretty easy. You can just say that your matrix type is AIJ MKL, or you can say that the matrix type, so Barry did something nice within the last year where he set up proper, proper subclasses of AIJ. So you can now set a C AIJ type, and you can say it's a sequential AIJ MKL is what I want to use whenever a sequential AIJ type is used. So you can set that. These options are a little bit different actually, because the latter option makes all sequential matrices default to the AIJ MKL, but the former option allows you to use a different sequential matrix type for like the diagonal and off-diagonal blocks in an MPI AIJ matrix. And the reason why you might want to do that is because you can leverage some optimizations in PETSc for 0 rows that often occur in the off-diagonal blocks that MKL does not have optimizations for. I also note, because people are always asking about using PETSc with some code that they say has to use threads, this does provide a possible avenue for thread support, because if you're spending a lot of time inside these sparse BLOS operations, MKL provides threaded versions of these. You can just link with MKL Intel thread, and then you just set this MKL num threads environment variable. And this will become more useful as we add as we start to use more of the sparse BLOS capabilities. I do want to point out, because I'm actually, let's see, I can't remember, Matt or Karl said, Matt said, we try really hard when we have an external package that we support, we really just want to support the latest version of the package. I'm actually supporting many old versions of MKL, and I think I agree with Matt, because it's been very painful to do this. But I was doing it because a lot of people were saying, well, I've got an old version of MKL, I can't just upgrade because I have to pay an expensive license fee. Well, now you don't have to do that. In the past year and a half, Intel decided to make MKL distributed free of charge, including for commercial users. So if you're using a really old version of MKL that I'm supporting, please go to this link and download the new one, because I think I'm going to drop some of the old stuff. I support the older versions, but the older versions actually aren't even that useful, because the versions prior to MKL 17 don't have the sparse inspector executor stuff, and they keep adding new things. Like in the most recent update to MKL, they introduced an optimized P transpose AP type operations for symmetric A. So if you're using something prior to that, it's not supported. And then once you've got your MKL installed, configuring to use AIG MKL is pretty easy. MKL is going to give you some setup script that you call that's going to set things like your MKL root environment variable correctly. And then once that's set, you just run configure and say, hey, my BLOS LAPACK directory is there. And then it should build with support for using this matrix class. So I mentioned the main reason I wanted to do this was take advantage of the sparse inspector executor stuff. That's what we default to using. I do know that you can disable that in case you want to do some experiments on how much that helps or hurts you. It's actually not very expensive. I've done a little bit of timings. Usually the cost of the inspection step is only about that of doing one matrix vector product. In PETSc, we're usually doing a lot with the matrix that we form, so generally you don't need to worry about that. The inspector executor routines do require building this, they call it an MKL matrix handle that's separate from the AIJ arrays that are used in PETSc. So if you really need to save memory, you might want to disable that and not use those. As for when I do the inspection, AIJ MKL defaults to doing lazy inspection. So it only performs this inspection phase like when it knows that I'm going to do something like a matrix vector operation and my matrix handle is either doesn't exist yet or it's become stale. And we track the PETSc object state to know when we need it to update that. If you want to force this inspection, like at the end of matrix assembly, there's an option for doing that. And again, please upgrade if you're using a really old one, because there's limited functionality when you're not using the inspector executor model. You might ask whether this actually buys you anything. The Intel folks, I need to get them using something else, because basically whenever they make some changes or optimizations to the routines in MKL, they just test against like a bunch of matrices. Like they have a bunch of matrices they like from, let's see, this is the Sweetsparse matrix collection. There's some Florida matrix collection. They just test against a bunch of stuff like that. And a lot of these are matrices with very weird structure. On these, they're showing pretty good speed ups compared to the MKL thing. So if you're using SLEPC to solve eigenproblems for some weird matrices, this might really help you. For more regular matrices that arise from typical PDE discretizations, right now I find AIG MKL tends to underperform PETSc's own implementations when we've used AVX 512 intrinsics, or when we're generating code using the Intel compilers. The GCC compilers and Clang compilers do a lot worse than the Intel compilers, so you may get a fair amount of speed up sometimes if you're using those. But I encourage everybody to try these out. I've been really pleased actually at the level of engagement that the MKL team has with this. They seem really interested in it, and they've asked me to tell them when I observe worse, cases like this where the Intel compiler is generating faster code than what MKL has. It should not happen, and they want me to tell them. So if we get more people trying this out and saying, hey, the performance is not very good, and then we can send the MKL team, point them to PETSc examples that don't get the performance they want. We want to do that because that's what they want from us. The idea is that hopefully, eventually, this stuff gets really good, and then the folks doing PETSc can worry about optimizing higher level things than the sparse matrix vector multiplication on whatever the latest Intel CPU is. Okay, so that's the two things I was going to talk about. There is another optimization that is targeting these many-core machines with lots and lots of CPUs. And Hong's going to talk about some of her work using MPI3 shared memory windows to do fast vector scatter operations. Oh, there it is.
Okay. Well, as Rich said, we have a many core machines, so definitely user keep asking us whether we can make use of the many core machines to use PETSc, kind of get faster speed, right? So we have to do those. So hardware trained to the large shared memory, like a KNL machine, we have like more than 60 cores with shared memory. And then the question to us is how to provide highly efficient on-node computation. That means how can we make use of shared memory to make our computation faster. So there are several considerations. Which approach shall we take? For example, right now PETSc is a pure MPI, right, distributed mode. And then whether should we use MPI combined with OpenMP or MPI Intel TBB, actually I don't know exactly what that is. Another approach is MPI and use MPI3 based shared memory. So for us, actually the last approach actually seems the most straightforward because with this approach, there's a minimum requirement actually changes in the PETSc library, and absolutely no changes for user application code. And also, we don't feel this way will kind of slower or inefficient than others. So we take the last approach, which is MPI combined with MPI3. That's what we choose here. Okay. So using MPI shared memory, most of PETSc inter-processor communication is happened in the vectorscatter. So that's a place we should start with. And then we have vectorscatter create, scatter begin and end. That's how the message gets sent and received. And then there's a destroy. So we look at how to use the MPI shared memory for scatter begin and end. The first one was implemented by Barry, and he basically used shared memory for communicating ghost pawns. Because when we use pure MPI, you put the ghost pawns into a local buffer, and then you issue send, the other process just issue the receive, right? That's the pure MPI pattern. So then we, instead of putting the message, the ghost pawn into the send and receive buffer, we put it in the shared memory, and the other core just read it directly. So this is the algorithm, pretty straightforward. So the first step is each core writes the ghost pound into the shared memory instead of write into the send buffer. And then this is critical. We have to put MPI barrier there to make sure all core finish the writing. And then each core can read it directly, because right now you don't have to wait and receive. You just can read to the shared memory directly. And then finally, we have the other barrier. I put here, this barrier can be skipped. Depends on where you call the wake scatter begin and end. For example, if you have a GM race algorithm, and then you want to send and receive the data, right? In that case, many GM basic KreeLog subspace iteration has like a wake norm, dot, and those already global synchronization routine. So with those global synchronization, you really don't need this MPI barrier here, because it turned out the MPI barrier is really expensive. So, but that one you must have. You have to finish writing and then you can read. Otherwise, there's a process. Go ahead and read it before the value has been written there.
So can I ask you a quick question? Does this write into shared memory if your neighbor that you're trying to ghost with shares memory, otherwise it just goes over the network?
Oh, actually it's a hybrid. We have an on node, off node. Okay. So here, this is for on node. See here is, let me see. Each core writes goes pound into shared memory. So we have, for example, on KNL machine we are using, right? There's a 64 cores shared memory. So we have to combine, it's hybrid. So if all those cores share memory, they do this. Otherwise, have to do the MPI send and receive.
If you've got this node and then this node next to it, that boundary still gets communicated over there.
Right.
And you handle that.
Yeah.
Okay.
Yeah, we can handle that. Okay. Right now, that's the original. So here we first detect whether I'm on node for this or not. And then waiting. Actually, it's a sub-communicator. So when all the cores in the sub-communicator, and then you do this share or not. If not waiting the same sub-communicator, you still do the all the way, send and receive, yeah. Okay, then here's the performance. So on KNL machine, we run small cases. I have to tell you the truth, we didn't get good performance. And on very, very large problems, so for example, here it's a 20,000 by 20,000 grid pounds on one node, which has 64 cores. So this is a shared memory without the distributed. And then for MPI1, that's the pure MPI. This is unshared. So you can see the ghost pound update, we only take about like 1/3 of the time. However, our objective is to improve matrix vector multiplication. That's how affect our application, right? And then the wake scatter only takes about less than 10% of overall matrix vector multiplication. So there's a very tiny gain for this case. And this only happens for pretty large problems. For smaller one, because MPI barrier. If I take away the MPI barrier, I got a really fast performance, but then you got the wrong answer, right? So, because see, it's not always in synchronization. So some core just write, some cores a little bit slow, and then the other core read it before it's written. So totally wrong, right? So for this case, you must have that MPI barrier. And without the MPI barrier, only very large problems, so we gain some gains, but not as what we thought. The smaller one is not good. Okay, then we tried a different approach. Okay, this is still the old one. So you can see for, this is a different problem. So this is an example. Actually, we have more balanced. So the ghost pound is like a neighboring, and then for still it's pretty large problem. 10,000 by 10,000, 20,000 by 20,000. And this is for the gain we got for vector scatter, and then the next is for matrix vector multiplication. So very tiny gain for matrix vector multiplication. We are looking for application which consume lots of the vector scatter. So for those cases, we make it a better one. Right. Okay, this is our observation. So for large data, MPI3 vector scatter accelerates. We got a moderate speed up for matrix vector multiplication. For smaller one, at least we realize MPI barrier is the bottleneck. We need to deal with that.
So
this variable is on the subcommunicator, right?
What?
It's a variable on real memory. Is it on the subcommunicator or is it a variable in the...
Vary for the communication.
Okay, but it's on the subcommunicator, intranode?
Internal, yeah.
Okay.
Now, see, maybe it's a job imbalance also. See, all the cores has to be in sync, and then we can go to the next one. Yeah. If I take away of this, everything is fast. You have to ignore the numerical results. Because see, it's a shared memory. All the cores can have a direct access. Unlike before, I have to send, and then you wait for, you receive, and then you can do something, right? But that ensures the numerical accuracy, the correctness. Here, you ignore who writes there. You just read it directly. Yeah. So we have used the MPI diary there. I think OpenMP, even though it's very easy to use, but the compiler or something has to do those log. And so that's why, see, I haven't heard anyone say NP is faster. It's easy to program, though. Yeah. So here, the second algorithm we try is to store entire vector in shared memory. So we introduce a new vector type called vector node. This is in PETSc new release. And then we have a different vector scatter type. So this type we call the MPI3. The previous one called MPI3, the old one called MPI1. By default, we still use the old one because we haven't been convinced this is better. So MPI3 node, and then I have two MPI barrier, one in the beginning, one in the end of this MPI scatter. And also I put here can be skipped. The first barrier to ensure all the cores finish previous work and then come down here, right? But sometimes this can be skipped. For example, again, if you use a KreeLog subspace iteration, before calling make scatter, you have done some norm computation or DAO, the synchronization computation. So this can be skipped, right? And then there's another one. When you finish, it's the same as the case for algorithm, the previous algorithm. This can be skipped if you are sure for KreeLog subspace iteration. There's a synchronization going on after this. So we have one in the beginning, one in the end. If you skip this two, we can get good performance. So we need to add some kind of flag to indicating when we can use this scheme, when we cannot. So basic idea this time is we put entire vector in the shared memory. And then each core can have direct access, right? Instead of just write the ghost pounds. So each core read unknown ghost pounds from shared memory. And then for off node, we can do send and receive. And then we do the local update once the local update. So this is the second algorithm. Then the performance this time for small size, again, my results actually all without MPI diary. If I add MPI diary, there's no performance there. So MPI1 compared with MPI3, this we got like a, so this is for matrix vector multiplication already. So we got about 30% acceleration. This I can get. This is small problems. For larger one, I can get the better. So this is still okay. The next line is the larger one, 800 by 800, and then we get good performance. For larger one, the performance is not that good, but still we have some acceleration for matrix vector multiplication. And again, here is now MPI. Now MPI barrier. Okay, so observation is we can get, for using this algorithm, we can get a matrix vector multiplication faster, even for small data set. And the new vector type we introduced, shared memory, actually can be usable for OpenMP or other type. So this is already in the PETSc library, and even though it's not as we anticipated, get a great news, like a good improvement, but still it's experimental thing, right? PETSc is a research package. We constantly try new things. Sometimes we succeed, sometimes we cannot reach to what we anticipated, but still it's an approach. Also, there's someone in the PETSc team trying different algorithms. But until now, if you have any kind of good ideas how to make use of shared memory for example, you have done this in your application and maybe some ideas we can borrow to improve it. The reason is the machine already there. the shared memory, many cores, and how to make use of those to accelerate our application, right? That's the key. So thank you. Oh, okay, here's an example how to use this. So you can try. You don't need to change your application code, just try like a big scatter type. The last one, you must use the right vector type. Yeah, that's the example. Oh, yeah.
No microphone, yes.
Yes.
See, look. Is there something like Control L? No.
If you download it and open it, you'll get proper full screen.
Okay. What is the
Click on it. Full screen.
documents? We'll do it. Here. No.
Someone claims F11.
Yes. Documents. All right. So, yes, so the last, we have 20 minutes-ish, is now dedicated to basically GPU functionalities in PETSc. Now, so GPUs is something like everybody wants to run on GPUs for reasons we don't always understand. Funding agencies, procurement centers. But there are also reasons why PETSc or any other libraries offering similar functionality have a hard time actually providing good GPU functionality. And I will sort of, so I'm not, even though I'm sort of attached to this GPU thing because I'm writing code for it, I still feel obliged to give you a fair and reasonable assessment of what can you probably get out of it and what is just wrong expectations and why you should actually don't worry too much about GPUs. And if you have a decent CPU solver, then just stick with that. It might be, well, it's definitely more productive than just like spending months in terms of finding out how GPUs work just in order to, once you know how GPUs work, you know that they don't work for you, probably. So, all right, so it's PETSc 2018. So I found this very nice slide from 2008. It's probably hard to see from anywhere, but very nearby. So this is sort of the early days of where GPUs came out. So CUDA can provide large speedups on data parallel computations straight out of the box. Even higher speedups are achievable by understanding hardware implementation and tuning for it. That is what the rest of the presentation is all about. So should be pretty easy. I mean, it's 10 years since CUDA came out, or probably 12 years. So we should have a decent idea about how to do that. Now, in 2008 already, they managed to get, for rigid body physics, a 10x CUDA advantage, whatever that means, speed up or time spent on programming. 10x, 15x on matrix numerics. For wave equation, it's like 17x. For biological sequence match, it's a 47x, which is probably more like a 20x if you look to the left. And then finance just goes all the way to the 197x. So this is straight out of the box performance, apparently. So yeah, if you see things like that, or if you have then people asking PETSc main, well, apparently I want to have 197x speedup because I'm doing applications in finance, but I can't get that with PETSc. So what is PETSc doing wrong? Yeah, then we have a hard time actually explaining what things are. So, and yeah, then at this point you probably just sit down, have a cup of coffee, you write your email, you enjoy your coffee, you delete the email, write it again, and then you point towards something that's similar to that plot, saying that, well, if you're reasonable and if you look at what performance can you reasonably expect for a given watt of power, Then you see something like here in the 2016 data. If you compare here a decent Xeon CPU to actual, so either a KNL or the Tesla P100, this was Karl GPUs, you see that in terms of performance per watt, there is no 197x. There is probably a 2x, but that's about it. So if you look at the right metric, which is performance per watt, then the best, or something you can reasonably expect, is probably a 2x speed up if things work out fine. Now, of course, you can run your Tesla P100 GPU with 250 watts and compare it to your laptop CPU. Then you probably get closer to your 197x speed up. But, well, then I recommend you compare your P100 GPU versus your calculations on a piece of paper, then you get even higher speed ups. So, well, we still have to care about those things because we have procurements, as I mentioned earlier. So we're going to live with NVIDIA Volta or Pascal GPUs in supercomputers for quite some time. And they will push us towards, so it's actually pretty easy to get allocations on those supercomputers if you actually say you have GPU code, because apparently most of the GPU resources are not as well utilized as they should be. But anyway, we're going to have Xeon PHYs, so NiceLanding, as Richard mentioned, and we're going to have GPUs around for quite some time. And if you look at memory bandwidth, which is sort of a reasonable first guess for any PETSc operations, then you also see that it's not enough to just run with a single core. You really need to do something like 10 to up to 100 threads on your node in order to get your full memory bandwidth. All right, so what is the current status? So if you download PETSc 3.9, and if you try to start using any of those Manycore things, so yeah, as Richard mentioned, just forget Knight's Corner, so the old Xeon Phi, which was a PCI Express add-on thing. On NiceLanding, since it's a self-hosted thing, it just works. So just works means it behaves like a normal CPU system. It gives you reasonable performance, as Richard pointed out, and you don't have to do any magic trickery. So with CUDA, you essentially configure PETSc and enable CUDA. We'll see that in just a minute. And then you can specify your vector types and your matrix types, and that will basically automatically take care of using the GPU whenever the operations are available on the GPU. And if one particular operation is not implemented for the GPU, it will automatically fall back to the CPU. So in that sense, you always get a result. In worst case, it just doesn't compute much on the GPU, but falls back on the CPU way too often. But you will see that on the performance logs anyway. Yeah, and then if you don't want to tie yourself towards CUDA too much, and you have the options of using OpenCL or OpenMP through the NRCL similarly by just providing the respective vector and matrix types. Please be warned with OpenCL, they claim, the claim is, OpenCL will just unify everything. You have this one library, and then you can target CPUs and GPUs and many cores. Yeah, that's an easy promise to make and hard to keep, and that's what you see in practice. Essentially, OpenCL on anything other than a GPU doesn't fly. I mean, it might be okay for FPGAs at some point in the future, but there are like other concerns to worry about.
Does set values work yet? Of those
yeah.
matrix types too?
Yeah, so it will buffer the values on the CPU, and when you do your mat or back assembly begin end, then it will transfer everything over.
Oh, okay, so it assembles on the CPU and then shunts it.
Yeah, because it still needs to build the whole communication patterns for matrix, for example, and that's sitting on the CPU anyway.
So you can really just change the matrix.
Yeah, it's really just a plug-in thing. So really just a plug-in thing means if you use some complicated functionality which hardwires the vector type to AIJ, you might run into an error, but that's something we can address in the future. So just let us know that something is hardwired originally. So yeah, configuration. Basically, you configure your PETSc installation as normal, as usual, and then what you need to add is with CUDA equals 1 if you're having the CUDA compiler available. If the CUDA compiler is somewhere sitting in a fancy location, you just provide the fancy location here. Similarly with VNaCL, which provides CUDA, OpenCL, and OpenMP backends optionally, you can just use the download VNaCL option, and then you can selectively enable either CUDA or OpenCL or OpenMP or any combination of those. So, in the interest of time, we skip the details on how it works in the background, but instead we look at some practical examples. So assume you have your PETSc configured correctly, everything went through. Now you're trying to reproduce your 197x speedup. Okay, no, it was sort of, this is matrix land, so this is a 10x speedup, which you probably expect. So if you run your example 12, that's probably some Poisson 2D example, and you run that with ILU preconditioner with just a single core, of course, because you want to have high speedups. You see that it takes you 629 milliseconds something for the GMRS optimization, and then you have 2.7 seconds overall for the solve. So that just as a reference point. Now, if you just do what I told you to do, which is you add vec type and then say VNaCL in this case, well, in that case, it will tell you no, my package PETSc does not support matrix type sequential AIJ VNaCL because the incomplete LU factorization, which is inherently sequential, is just not supported in that particular case. So, okay, we have to change something. Now, since the ILU preconditioner is the problem, let's just turn off the preconditioner.
Karl, if I were a random user, how do I know from that message that ILU is the problem?
Well, it's a mat solver package. Okay, yeah, probably. That's just part of the stack trace. Sort of in the context, sort of the error messages above and below, they contain ILU as the culprit.
Because it's all, because I mean,
from that line alone, it's
impossible. Right?
But you get more than just one line of PETSc error if you run into an error. But there's just so much space on the slide. Okay, so let's turn the precondition off. Now all of a sudden it takes 16 seconds for the solve. But now you can run it on the GPU, and now all of a sudden your KSP solve only takes 1 second, and bam, you have 16x speed up. And everything is fine, right? Okay, now let's look into the details. Well, first thing is, if you probably remember with ILU, the solve time was just 2.7 seconds. So if you then compare that to the 1 second with GPU, it's not a big leap anyway. But what are the issues we are fighting with? So sort of the biggest issue we always encounter is just GPUs are sort of too fast for PCI Express these days. So with latest GPUs, you get something like 720 gigabytes per second of memory bandwidth on the GPU. So once your data is on the GPU, things are really fast. Whereas with PCI Express, you just get 16 gigabytes per second. So the bandwidth you have available for sending your data from the CPU to the GPU is just a factor of 40 smaller. Well, now, if you just set up the data once and then you do your computations and at the end you get the results, you might think, oh, that's fine. Now, let's look at an example. Say you want to solve a Poisson equation on 3D with lots of MPI ranks, and each MPI rank basically takes care of one such cube of the discretization domain. So sort of a DM, regular DM, and let's take n something large, but not unreasonably large. So let's take n to be 512. So if you have a field defined on the whole domain, then that takes 1 gigabyte of GPU RAM, so that's sort of filling up the GPU nicely, but it's not overfilling up the GPU. And yeah, if you do anything reasonable with PDEs, then you need to have boundary exchange at with the ghost layers. That means with the MPI rank neighbors, you have to exchange the values here on the faces. Now, how many faces do you have? So each face has n squared grid points. Then you have 6 faces. And then because you're communicating back and forth, it's a factor of 2. So you have a total of 31 megabytes that you need to communicate for the ghosting. So, so if you process the whole field on the GPU, so everything on the whole n cube cube, it takes you 1.4 milliseconds, and sending just the boundaries through the PCI Express layer, PCI Express link, takes you 1.9 milliseconds. So even in this case, where the volume to surface ratio is really very much in favor of the GPU, you're basically dominated by ghost value exchanges. So your 40x imbalance in terms of memory bandwidth is really giving you a hard time to do anything reasonable, unless reasonable in terms of things that work well on the CPU. If you try to do that on the GPU, you just run into those kind of problems. Yes,
in the absolute terms, if this number, you know, if the computation were free,
yeah,
like your floating point operations were free on that cube, would this 1.9 milliseconds still give you a win over doing it on the CPU? Or are you losing?
So it depends on what you have available for a CPU. So if you have something like, say, a KNL available, then you have high bandwidth memory, and you have like 480 gigabytes per second of bandwidth on this, what's called CPU side, then it's hard to win with a GPU. If you just have a very weak old Xeon CPU sitting there just to basically manage the GPU, it might still be worth using a GPU. And I mean, we have some supercomputers where basically the GPU is sort of the big star, and then there are those like tiny CPUs just to keep those things running. So a couple of, I could think of, maybe there are some, say, ARM computers coming up where basically they're using the ARM processors just to coordinate the GPUs, and then the workload is done on the GPUs. If you have like very compute-intensive stuff for the GPU, that's fine. But for PDE type of things, where you actually need to exchange boundary layers every once in a while, that will still be a tough application. Okay, so then pitfall 2. This is probably the most commonly encountered issue we find on the email list. So you need to pick the right data sizes for GPUs to fly. So if you have a very small data size, and that's usually sort of the thing you start with. You start with, oh, I take this small toy problem, I run it on the GPU, and now I don't find my 197x speedup. So reason is something that Richard already mentioned. If you have very small systems, you're totally limited by latency. So just the time it takes the CPU to talk to the GPU and say, please run that kernel for me, will always like level off in terms of performance here. So all those GPU codes you usually see are just completely level off for not too small system sizes. Now, okay, you can always argue that you want to do weak scaling, so you increase your problem size. But even then, your GPU RAM is limited to a couple of gigabytes. You don't have any fat nodes where you have 512 gigabytes of memory or a terabyte of RAM available where you could just keep scaling out. So either you're probably limited by latencies, or you just don't have enough memory available. And you need to know what you're doing in order to stay sort of here in this sweet regime. Okay, so turning that graph from the previous slide the other way around, so if you want to do strong scaling, if you have a hybrid cluster, anything that has a CPU and the GPU merged together, and if you want to run it in a hybrid fashion, you end up with some reference line, which of course, as you increase the number of processes, at some point it will just go back up again, so simulation time will go back up. But if you have just a pure CPU cluster, then you don't have the extra PCI Express latency. So even though you might need more processes to get your strong scale minimum time to solution, because you might need, say, 16 MPI ranks instead of just one that feeds the GPU, you might still, it's very likely that you end up with a smaller total time to solution. All right, then there are some composability issues. So, I mean, passing function pointers around, passing memory pointers around is something that the NVIDIA compiler does a good job of hiding from you all the tricky details in terms of how to generate the right GPU code in your application. But if you're actually really building a library stack, then at some point the NVIDIA compiler just runs out of magic, and then you have some issues with really composing things. I don't want to go into all the technical details, but composability is quite a beast with GPU codes. So the frank evaluation of GPUs is, so many non-trivial PETSc operations do not benefit from modern high-end GPUs in a substantial way. So important is non-trivial and a substantial way. So by substantial, I mean a factor of 2 at least. I mean, I'm not talking about a factor of 10, but if you're frank in terms of performance per watt, you're more than a factor of 2 is unlikely because of the very early graphs we have seen anyway. And I mean, considering that you could do just proper science rather than trying to run something on some other hardware that will ultimately give you the same results anyway, yeah, it's just nothing we can recommend to a broad audience. If your research is all about running stuff on GPUs efficiently, please look into it. But if you're just interested in getting your science done, please just don't spend too much time on GPUs. All right, overview of functionality. In the interest of time, since it's 25 o'clock, please keep that part. Just mention upcoming features for the next PETSc release. Yes, so we actually, so the last PETSc release, the 3.9 release, was the first one with GPU functionality unlocked in the release. Earlier you had to pick the master branch to do that. Now we have kept out a couple of features that were in the old master branch, but that were not considered sufficiently stable. We want to sort of add those things back in, but in a stable way, and add a few other things. And those other things are GPU accelerated GAMG, so the AMG functionality in PETSc that should get GPU acceleration for the finest level where there is enough data to process. And in that context, it's also NVIDIA's AMGX package, which is now available as open source. It's sort of much easier now to interface. We want to add that as well. And then for VNSDL, there are a couple of like low-level plumbing things left to be done. And with that, it's the conclusion slide again. Thank you for your attention. I'm sure it was hard enough to keep listening all the way up to 5 o'clock. Now you're sort of freed from your duties. Thank you very much. If you have any questions, please go ahead. Dave, yes. No, that is one of those things where the preconditioner just inspects the matrix. It sees that, oh, this is a GPU matrix, and doesn't know what to do with the GPU matrix, and then it just errors out.
Oh, there's no code. What you need is code that would say, oh, I can act on the CPU, and then you have to push the result of my action down to the CPU every time. Right. So you could do that. We have no code that does that.
We do have actually another option. So there is a ILU factorization in Sweetsparse implemented. So you can just take a PC type is ILU with a Sweetsparse factor package, and then things are fine.
Yeah, at the end of your board statement, you said it was printed open power might be an exception.
Open power.
Can you just tell a bit more?
So the reason with open power systems is that they have the NVLink bus, which has about 4 or 5x the bandwidth of PCI Express. It has, I think, a comparable latency, but at least the bandwidth issue is not hitting you that hard. So it's sort of your sweet spot is a little larger. Plus your I have to be careful with the statement, but With open power systems, you have not Xeon CPUs sitting there, but you have power CPUs sitting there. So it's your sort of per core performance is slightly different. So you would have to optimize for your CPU in order to get a decent CPU performance as a reference point. And so it's probably easier to observe speedups on open power systems for these two reasons.
But you still wouldn't recommend to use GPU in open power systems?
Well, if you use an open power system, then your system provider will feed you to use GPUs anyway.
Okay.
Because they have the GPU sitting in there and paid a lot of money for it. So. Patrick.
So normally when I have a conversation about GPUs and PETSc, it gets down to the point where I say, well, what you want to do will probably work, but you're going to have to write some kind of a custom kernel yourself. Is there a path for users to do that in a sort of way that doesn't require you to be any kind of GPU expert? Like, can I do this through NiceLanding? Can I do this through some CUDA library?
So what you can what you can always do is you can grab the memory handles out of the objects. So you can say, like, give me the CUDA buffer where all the vector entries are located in, or the matrix arrays. And then you can do whatever you want in your matrix-free methods, for example. But you still need to have a reasonable understanding of what to do with those buffers.
So like say that I could follow the NiceLanding example and write my own.
Yeah, you can do that. Yeah. Yeah. So basically, you can basically just use all the external library functions that are there anyway. Yeah.
Okay, I think we should wind up. We are now over time. So thank Karl and Hong and Richard again for that last session. We'll just stop the recording. Find where the thing is.